Hello everyone. The subject of this talk, titled The Role of the Investigation Projects in the Definition of Sites of Geological Interest, comes as a result of the research projects carried out within the LIGS Canarias project, in collaboration with doctors Inés Galindo, Nieves Sánchez, Juana Vegas from the Geological Survey of Spain, and Esther Martinez from the Museum of Natural Sciences of Tenerife. One of the first tasks in the geological heritage study of a region is the selection of sites of geological interest and the production of a catalogue where those sites found with greater heritage value are gathered. Obviously, the greater the geological knowledge, the better and more comprehensive the catalogue will be. It's very common, however, that not all areas of territory hold the same level of scientific information. This is what happened with Mazo, as it is a cone of monogenic scoria, not very well known, that shows singular features which oblige us to change the idea once held about the factors and processes intervening in the construction and evolution of this type of volcanic edifices. The Mazo volcano is located in Lanzarote, an island that covers a small area, just about 845 square meters, situated in the northeastern sector of the Canary archipelago. Just like some other islands of the archipelago, Lanzarote has a volcanic genesis and an essentially basaltic nature. Lanzarote has a simple geological history which is characterized by the presence of two ancient volcanic massives, found in the northeast and southeast, and a central area made up of a volcanic field, with more than 150 monogenic cones. One of the most characteristic geological elements of the island is the development of two historical volcanic eruptions happening in the central western sector of the island. These two eruptions were multiple and fissure type, with fractures ranging from 14 to almost 17 kilometers in length. The Timanfaya eruption, lasting almost 6 years from 1730 to 1736, during which process 300 eruptive mouths were created and about 30 volcanic cones built. Some of them, belonging to different phases of the eruption, are found overlapped on the same place. And then we have the eruption of 1824. They both were fissure-type multiple eruptions, but very different in regards to development, because while in Timanfaya more than 30 volcanic cones were created, in the 1824 one, only the volcanoes of Tao, Nuevo del Fuego and Tihuatón were formed. The island of Lanzarote, depicted in this map created 3 months after the first eruption, had a population of 4,765 inhabitants before the eruption. However, within 3 months, 44% of Lanzarote's inhabitants had already left the island. 58 villages and population centers were completely destroyed. 35 of them where the 300 eruptive mouth openings were, and the other 23 due to ashfall. Fortunately, from the records gathered, only 1 human life was lost. Some records from the eruption will also allow us to have an idea of it. Let's not forget that the volcanic activity wasn't constant, with a combination of eruptive and quiet phases lasting almost 3 months. Nevertheless, a great part of the whole eruptive system was built over the first year. As we can see in this slide, the greater part of Timanfaya's eruption and the 2 latest events from the 1824 eruption are included in the global geosite named A Recent Volcanism of Timanfaya, Lanzarote, forming part of the global geosite inventory of Spain that was produced by the Geological Survey of Spain. In the geopark of Lanzarote and Chinijo archipelago, 17 sites of geological interest represent the historical volcanic activity in the island, including edifices, lava flows, and pyroclastic deposits. During the making of the inventory of Lanzarote and Chinijo archipelagos geopark, the work team carried out an inspection of the insular geology and several field campaigns were performed, with the aim of selecting and establishing the sites of geological interest in the island. During these campaigns, 17 sites of geological interest were selected, all linked to the Timanfaya's eruption, most of them with mainly a volcanological interest type. Specific sites of interest were also detected, places that lacked of previous detailed studies. One of these enclaves belongs to the Mazo volcano, a mafic scoria cone that can be found in the central volcanic field of Lanzarote, located in the north of the main eruptive fissure of the Timanfayas eruption, and whose origin from the eruption was questioned by some authors. Hence, geologically speaking, this cone was placed in the group of those with doubtful allocation to the 18th century eruption. Previous existing studies on Mazo describe this volcanic edifice as a scatter or scoria cone in a horseshoe shape or amphitheater that's undergone a process of rusting, with several craters from where lava flows poured out in blocks, resulting from a Strombolian activity. However, the high asymmetry of this scoria cone, its morphological features, as well as the deposit characteristics, enables us to establish a more complex eruptive history. The Mazo volcanic group is actually a monogenic cone of very recent scoria whose amphitheater morphology resulted from a collapsing process that gave origin to the formation of several avalanche flows. A side of the cone is configured by layers of welded pyroclast, lapilli, and bombs of some clastogenic lava on its base, identifiable on the inner walls of the supposed craters. All these deposits are affected by intense fracturing. As we can see in this diagram, only the south flank of Mazo retains its original edifice morphology. The rest of the volcanic cone is now completely unstructured. The proximal areas are made up of turriba block facies, basically composed of pyroclastic layers, scoria, and clastogenic lavas. These blocks appear arranged in a rift valley displaying amphitheater morphology from where a debris avalanche deposit, also known as DAD, develops and spreads towards the east, northeast, northwest, and west, covering an area of 1.2 square kilometers and reaching a maximum distance of 1.6 kilometers. The deposit thickness is difficult to estimate, but minimum values of 35 meters in the proximal areas and of 5 meters in the distal one can be assumed, which correspond to broken pieces that have slid from the cone, slightly unstructured and teared and divided by inter-turriba depressions through common faults and rift valleys. A conjugate fault set can be observed in the southeast flank that is inserted in a listric fault plane, identifying several turriba blocks. The east and north flanks are formed by several huge blocks made up of lapilli and scoria, as well as pyroclastic deposits. Towards the north and east of the volcanic edifice, in a steep slope area, there are debris avalanche deposits arranged in various identifiable flows with well-defined lobules and steep fronts. It's in these sectors where the deposit has the greater amount of hummocks, most of them in an elongated shape and arranged parallel or transversal to the flow direction. As we can see on this slide, in distal and mid areas, the deposit shows a hammock topography with plenty of transversal and longitudinal ridges, over where a giant 43-meter tall mega block stands, located at about 500 meters away from the amphitheater. This isolated megablock, found in the middle of the deposit, is composed by a stratigraphic sequence of various stacked lava flows, hydromagmatic deposit with a paleosol and a calcrete on the top side with terrestrial gastropods, and finally a volcanic spatter deposit made of clay injections. We can also see an unstructured part of the megablock in a scoria deposit. All these features make us believe it to be a substrate block. Part of the block was covered by lava melted during the seeping of debris avalanches. The rest of the deposit, the avalanche in this sector, is chaotic and irregular, and is made up of mixed facies with debris and blocks ranging from millimeters to hectometers in size. Broadly speaking, the deposit is class supported and polymictic, with polyhedral clasts of massive dense lava, vesicular lava, welded scoria, hydrovolcanic deposits, and fragments of carbonate crusts and paleosols. Blocks and clasts usually appear fractured with jigsaw cracks and grooves, and with structural deformation due to impact. As the picture depicts, the presence of injection structures in the mixed facies, more or less distal, such as squeeze-ups with avalanche clasts among the fingeries and back grooves, or injected lava among the DAD clasts, are signs of the presence of a ductile basal layer of low viscosity. These structures are found along a zone of slope rupture, suggesting they were formed due to the compressing processes occurred during the avalanche seating at the time of the adjustment to the slope where it ran. These elements point at a syngenetic avalanche. In the most distal area of the avalanche deposit, the most outstanding element is the presence of decametric blocks, mainly made of scoria, that have a significantly more reduced size, less than 90 cubic meters, which can be found in the middle and proximal areas. The DAD deposit is covered by a blast composed by three phases. One comprises big volcanic bombs of up to 40 cubic meters, made up of fragments of the avalanche deposit, and extends up to 500 meters from the emission area. The second layer is formed by a clast deposit of up to 84 centimeters in colors ranging from gray to whitish, with clast supported, well arranged and normal, sizing from gravel to fine sand, with parallel laminations and low content of juvenile fragments. Lastly, covering all the previous deposits and adapting to the topography, a layered deposit ranging from gray to yellow in color, matrix supported and with wavy lamination formed by hydromagmatic surges. It is bare exposed in proximal areas with a thickness of 40 centimeters, thinning down to a few centimeters in distal areas. There is clear evidence of hydrothermal alteration associated to the fractures within the reef valley. A deposit made up of oncolites of decimetric size. The diffraction of X-rays has shown that these oncolites are formed by a lithic nucleus covered by hematites, surrounding layering of between 2 to 6 sheets made of native sulfur, gypsum, geosite, and minor anhydrite, a white sheet formed by shapeless silica and opal A. Its presence provides the definite assistance of high temperature vents. Finally, the entire avalanche deposit is found vastly covered by a lapilli layer that shields the topographic irregularities and homogenizes the geological landscape of Mazo. Although some authors have proposed some evolutionary sequences that interpret Timanfaya's individual eruptions by means of combined analysis of historical data, chronostratigraphic, geomorphological analysis, and geological cartography, there is still uncertainty about the when, where, and what volcanic processes took place in each of the multiple eruptive vents developed throughout this almost 60 years the eruption of the 18th century lasted. This is the case of Mazo volcano, whose age is still quite controversial. For the study referring to the age of Mazo volcano, the information gathered by José de León regarding the location of the destroyed villages during the eruption has been a key contribution. In this research, basically all places close to Mazo have been studied, which have enabled us to carry out a more detailed reconstruction of what happened during the first months of the volcanic eruption. Although in previous works Mazo has been considered as an approximately 1,000-year-old volcano, and therefore previous to Timanfaya, the data obtained in this research in reference to its geological evolution, including the collapsing of cones and the generation of debris avalanche flows, along a new review on the chronicles describing the eruption events, allow us to confirm that Mazo is actually a volcanic cone created during the Timanfaya's eruption. The sequence of events happening over the first months collected in the scientific researches only talks about 3 volcanic episodes aligned in a southeast-northwest fracture. The one from La Caldera de los Cuervos, from the 1st to the 19th of September, the Caldera de la Rilla episode taking place from the 10th to the 31st of October, and lastly the Pico Partido one, happening on the 10th of October 1730 and also on the 16th of January 1731. On the 11th of September, the emitted lava flows from the first eruptive center in Caldera de los Cuervos completely destroyed Mazo village. Most chronicles narrating the eruption point out that after a large earthquake taking place by mid-January in 1731, which effects were felt in Gran Canaria Island at more than 190 kilometers away, on the 20th of January 1731, a new volcanic episode began. In the Simon's manuscript, one of the most extensive and accurate documents, it's described that this new eruption was located in the place where Mazo village was, already burnt down and destroyed by the lava coming from the first volcano of Caldera de los Cuervos. Although with some mistakes in reference to the date of the eruption, the priest from the village of Jaisa, the best-known chronicler of the eruption, narrates the edifice collapsing in its own crater, the formation of an eruptive column that covered the island of stones and ash, and the forming of incandescent currents that reached the sea. It's evident then that the geological as well as the documented data are referring to a volcanic episode that can only be that of Mazo. Therefore, the set of Mazo corresponds to the fourth event of Timanfaya's eruption. From then on, the different volcanic episodes will occur in the main fracture heading east-northeast, west-southwest during the rest of the active period. Summarizing, the eruptive history of Mazo volcano depicts the existence of at least 4 different phases. The eruption started after an earthquake of high magnitude on the 20th of January 1731. Initially showing a Hawaiian activity, as seen by the fragmented scoria outcrops and cloudogenic lava present in the preserved original edifice, on the Turiba blocks, and in some hammocks of the avalanche deposit. Later on, the eruptive style changed into a strombolian behavior. Hence, a cone of scoria taller than 200 meters was formed within just a day, as it can be read in the chronicles. The speed of the initial cone construction reveals high eruptive rates. This way, part of the collapse could have been favored by the processes of accumulation in the cone, which made it grow extremely fast, pushing its stability limits. Once this limit was exceeded, small mass additions could have triggered the landslides as debris avalanches. What's more, the presence of a great amount of lava in the crater and at the base of the cone could have also promoted the collapse of the walls. However, the doming process doesn't seem to be the collapsing cause, as the faults and fractures affecting the cone do not follow a pattern associated to intrusion and inflation processes, although it can't be ruled out either, as the original fracture pattern has been erased during the edifice displacement. During the second phase, the cone fracture occurred through a normal fault that affected not only the cone but also the substrate on which it rose, promoting the collapsing of a large part of the edifice, including parts of its summit and substrate. In Mazo, there is well-defined fault in the cone, parallel to another normal fault that affects the recent deposits of Timanfaya, with a fault displacement of at least 45 meters, suggesting a structural control. These faults are also parallel to the main eruptive fissure of Timanfaya. The tectovolcanic processes, as triggered for the collapsing of the cone, are also supported by the large distal megablock included in the DAD. The cause of the cone breakdown in the north sector of the edifice could be linked to not only the influence of the stress fields inside the volcano, but also to the regional tectonic tensions caused by the shift in direction of the fractures between the first and second eruptive phases of Timanfaya. Moving on to phase 3, The collapse of the flank caused a debris flow where two different domains can be discerned. A torriba domain, higher and closer with fractures arranged just like a graben and perpendicular to the collapsed direction, and a hammock domain in the lower part of the collapsed flank. The presence of these two sectors could be related to the existence of low viscosity basal layers and ductile behavior in the substrate of the volcanic cone, which will be located during the movement under the hammocks domain, as it was proven in the processes of lava injection on the hammock and on the formation of squeeze-ups in the avalanche sector subject to compression. In the monogenic mafic volcanoes, the existence of basal layers made of sputter emitted during the initial stages of the eruption and subject to loading processes by accumulation of subsequent pyroclastic rocks has been used to explain the rafting processes of the volcanic cones. In the case of the collapse of Mazo flank, this layer could belong to sputter emitted during the initial phases, setting the base of the stratigraphic sequence in a way that the heavier the volcano, the greater its plasticity, hence the collapse. In any case, some analog models show that the deformation of the base is necessary for the formation of collapses affecting the substrate. The features in this deposit are equivalent to those observed in stratovolcanoes, with the proximal area characterized by the presence of block facies, whereby flows of much more fractured material were located on steep slopes and relatively short paths, while the most disaggregated material, due to the friction between blocks, fluidized by the presence of melted lava, reached a greater distance, producing more dispersed hammocks, smaller in size. The collapse formed an amphitheater of 500 meters in length in the north flank of the cone, and a DAD that, according to the chronicles, reached the sea on the coastline far more than 6 kilometers away. The cone and deposit's volume is impossible to calculate, as they are partially covered by lava from subsequent eruptions. And finally, on phase 4, the decompression caused immediately after the debris avalanche resulted in a cloud of explosion and ballistic missiles made of heavy blocks and bombs that were shot in proximal areas and up to 500 meters away from the vent. This explosive cloud was a gravity flow, likely divided in two parts. One of them, a basal flow composed by coarse grains of rock fragments, and the second one, a higher turbulent fine-grained flow, which originated a pyroclastic wave that covered all the preceding deposits. This deposit from the explosion has been found up to 6 kilometers away from the vent, and based on the historical chronicles, the finest grained fragments affected the entire central area of Lanzarote. This deposit covered the DAD, but nowadays it can only be seen in the areas where it suffered hydrothermal alterations. That is to say, on the still hot torriba and hammock blocks, or where it was buried by pyroclasts from the last stages. The hammocks and squeeze-ups hydrothermal alterations in the DAD also back up the theory of this being a syngenetic collapse. Besides the implications that Mazo's eruptive history has in what to the eruption of Timanfaya refers, this study allows us to draw at least 5 main conclusions. On the one hand, a Mazo volcano shows features and morphology similar to those described to characterize the processes of volcanic instability taking place in large volcanic structures. Secondly, Mazo illustrates that flank collapses are not uniquely linked to stratovolcanoes, even though the size of the amphitheater and avalanche deposits are significantly smaller in monogenic volcanoes. Number 3, Mazo is an example that during the construction of a monogenic scoria cone, volcanotectonic processes can trigger a flank to collapse. Number 4, the morphology of Mazo volcano and its well-exposed DAD deposits makes it a unique and ideal case study to characterize this type of process in mafic monogenic edifices. And last but not least, the development of debris avalanches and the generation of high-altitude eruptive columns associated with Mazo volcano forces a change in the perception of the hazards linked to the growth of monogenic volcanic cones. From the perspective of the studies regarding geological heritage, the following considerations should be taken into account. The basic investigation constitutes an essential preliminary step to the site of geological interest characterization in any territory. Mazo is a good example for the natural heritage management to comprehend that the heritage inventories are open lists and that any new research can reveal the existence of geosites of great scientific interest at a national scale. The strategies in the management of geological heritage must include the promotion of new geological studies of the territory. As a result of a scientific study on Mazo volcano, it has now been included in the Geological Heritage Inventory of the Canary Islands. And since it's the only study known in the world on syngenetic debris avalanche in a monogenic volcano, it has also been recommended as a global geosite of international relevance for Spain. And finally, this is a picture of the workforce mentioned at the beginning of the presentation, dedicated to the geological heritage and the geoconservation of volcanic insular territories. They are the ones who have established the geological basis for the candidature of the island of Lanzarote to become a UNESCO Global Geopark. And that's all. Thank you very much for your attention.